discussing all the different types of interactions that we need to think about and worry about in biological systems. One of the important building blocks of amino acids and proteins in general is the amide bond. CONH. What does it correspond to? It corresponds to a dipole. Okay? So all amino acids are proteins that are linked together by strong covalent bonds involving this object here. Every amino acid has a side chain. There are 20 of them. Different chemical groups. Alanine is CH3. Others, it's a different object. Okay? So I gave it this excerpt because you should be very comfortable for the exam to be able to draw out those types of structures. Okay, it's very simple. It's very easy. And if you can't remember the chemical structures, I don't care. You don't need to know the chemical. What I care about is if you're able to tell me, okay, I have a dipole, and then on the left side I have something that's charged positively, on the other side it's charged negatively, and how it changes as a function of pH, for example. Okay, that's the type of thing that you should be comfortable being able to answer. Okay, so we're now going to build on these ideas and start talking about the protein folding problem. Okay, so the protein folding problem is illustrated here. I have an amino acid sequence, protein. It's interacting with its environment, the bath. It's also interacting between itself. And something happens that takes the protein from its unfolded state to a folded state. So the classical, simple way to think about it is a two-state model. I go from unfolded to folded. It's much more complicated than that, but that's the starting point. That's what we're going to partly discuss today. Okay? Now, those dipoles, remember, on the backbone, the reason we emphasize it a lot is because those dipoles, when they're in a bath, in a liquid like water, they will form dipole-dipole interactions. Okay, so there's a reason why we need to understand what the chemical details, the chemical groups are, because then you can make sense of what are the relative energetic changes that occur when a protein folds. Because when a protein folds, for example, this NH group might get buried inside here. Okay, so you might say, I lose energetic, enthalpic energy. I lose enthalpy taking that dipole, this NH group, and burying inside. But many times that's compensated because of hydrogen bonds or other dipole-dipole interactions that take place within the protein. Okay? We also discussed understanding electrostatic interactions in liquids, and one of the most important things that we need to remember is how charge-charge interactions scale as a function of thermal energy. So if I assume that I have a continuum dielectric, I can estimate at what length scale does the electrostatic energy get much larger than kBt. Okay? That length scale is called the Buron length. That Buron length is dependent on temperature, is dependent on dielectric constant. Okay? So depending on temperature, dielectric constant, the Buron length will change. In water, that estimate of the Buron length is about 7 angstroms. Okay? Okay. So electrostatic energies in liquids, because of screening, of course depending on whether it's a dipole or liquid or not, will change the length scale and the energy scale associated with the interaction. Okay? And if you go back to the thing we talked about several lectures ago on the convergence of energy scales at a particular length scale, thermal fluctuations at ambient conditions allow for the efficient interconversion of energy between, for example, thermal energy, elastic energy, electrostatic energy, and also electronic energy. Okay? So there's a reason why these length scales are special in the context of biological systems. Okay, so that was one thing. We've also discussed this at length. I'm just reminding you again. Van der Waals interactions are also important in biological systems. Van der Waals interactions are very weak. Okay, but when you have many of them, they can all collectively add up. And Van der Waals interactions scale as 1/6, okay? And they come from induced dipole interactions. Okay, fine. So that's a bit of review. Do you have questions before I move on? Okay, so this is very, very succinct and very brief. I'm not going to get into the details of this, but they are proteins, when they go into the cell, undergo changes. So if you have a sequence, a primary sequence of amino acids, remember it folds into a protein. As it moves along, it will not remain in the same chemical form. There will be changes that occur to it. And so there are lots of different types of changes that happen to proteins, and these are known as post-translational modifications. One example, give me a second, one example that we discussed, remember, the application of bacteria living in volcanic vents, able to survive very high temperatures. One of the reasons of that is they have these post-translational modifications known as disulfide bonds. These are covalent bonds that link regions of a protein that usually just interact through Van der Waals interactions and dipole-dipole interactions. But now you have a strong covalent bond. Why is this important? Well, if I yank up the temperature, like I would need to do in a hot environment, this is less likely to denature or unfold. Okay, so this is one example of a post-translational modification that happens to a protein which allows it to adapt to its conditions that it's living in. Question?
Do you mean proteins move into a cell, or they just created inside the cell?
Proteins are generated inside the cell, then they go out of the cell, they make up. So everything about you is a protein. Your muscles are protein, your hair is protein, your eyes are protein, it's everywhere. Your nails, you name it. So it's nothing that you can say that they're, localized in one place. They're the building block of everything.
I thought they maybe generated inside. Yeah, not moving into.
No, I don't understand.
No, because you said when proteins move into a cell, we have some modification. And I'm wondering, do they move into the cell, or
they can come in, they can come out. They're yeah. So the cell is one aspect of biology, but then there are many other things. For example, where proteins are needed outside of the cell, okay, to build different types of architectures and different types of functionality. Okay. Another modification that I'll just mention to you is that often in many biological systems, you have this complexation of an ion. So this is an example of a system where I have a lot of negative charge. Okay, I have a lot of negative charge, and if I have a lot of negative charge localized in one region, and I need to stabilize the system, well, what's it going to do? It's going to find a way to put some positive charge in there. In this case, it's a calcium ion. Calcium ion that stabilizes the negative charge. Without the calcium ion, the thing would not be stable. Okay? So, before it adopts this type of architecture, these groups would be far away from each other. But by putting in a calcium ion, you're able to bring lots of negative charge close to each other. And so this is one of the things that makes biology very interesting, but also rather challenging. Because the standard rules that we learn in physics, which is, well, the positive charges, like charges, will repel each other. Okay, but then you look at this and you say, well, these guys come very close to each other. They come up to 3 angstroms, 2.5 angstroms. How? Why? Well, because you have very specific interactions that essentially screen the repulsion between the two charges. Okay? So this comes up again and again in biological systems. Okay, so I'll skip this and move on now to the protein folding problem. We've been building up the ideas associated with this, but I just want to repeat this again. What is the protein folding problem? Okay, I have a spaghetti chain. It's made up of amino acids, and for many proteins, in order to perform their function, this spaghetti chain must shrink. It must fold. It must compact itself. That process, how and why, what is the thermodynamics and the dynamics associated with taking that spaghetti chain and making a folded structure, is the protein folding problem. And the question that people ask is that a random process? Or is it not random? Is it directed? Is it guided in some way? Are there specific pathways that along which it goes and others that are blocked? So that's the question. And so many people in the physics and the chemistry community are interested in trying to solve this problem, because you want to come up with a fast algorithm, a fast recipe for it. I give you a sequence of amino acids and say, tell me what the three-dimensional structure is. Okay, now, do you think it's random? No. Why?
Maybe it's unique for every specific function that a protein is associated with a certain protein.
Let's keep it general. So let's say, a protein with 100 amino acids, unfolded. How long would it take to fold if it was random? As a guess. How many?
10 years.
10 years.
It's something about in the range of years, right?
Actually, some proteins do take on the range of years to misfold, but this is a pathological problem. Okay, do you remember the Ramachandran plot? Yes? You remember phi and psi? Okay, so phi and psi are order parameters that allow you to distinguish different states. Okay, so I have an amino acid or a peptide, and these dihedral angles, these phi and psi's, allow you to distinguish between alpha, beta, etc. Okay, so let's imagine that there were only 2 or 3 states associated with each amino acid. Yeah, that's it. That's a gross underestimate, but let's say there were only 2 or 3 states. And let's say it took, a femtosecond to sample each state. Okay? Now let's imagine that I have an amino acid, a protein made up of 100 amino acids. If there are 100 amino acids, how many dihedral angles are there?
The total possibility.
Yeah.
2 to the power 100, 3 to the power 100, 2 or 3 to the power 100.
Okay. So now let's say each state was sampled in 1 femtosecond, which is not going to happen. But let's say it was. You already see that it's a very simple argument that the protein folding process, sampling only 2 or 3 microstates at 1 femtosecond each for a long sequence of minutes, would take the age of the universe to eventually find the configuration that is folded. So it's not going to happen. It's not going to happen randomly. Yeah.
Why is it important to fold the proteins?
Okay, good question. So, why is it important to fold the proteins? So, let's go to something like this. Okay. So, this is the folded structure of a protein. It has these helices and these sheets, and they form some three-dimensional structure. The three-dimensional structure, for example, here this is myoglobin. Myoglobin is a protein that has heme. It's an iron group. It's a chemical group that has iron, and this is the thing that binds to oxygen. So myoglobin's function is to bind to oxygen. Without having this three-dimensional fold, there's no stable place for the heme to stick in. There's no place for the oxygen molecule to stably bind to the protein. So the folded structure of a protein is needed to perform its function. For most proteins. Without the folded structure, the protein cannot perform its function. And this is related to the fact that by folding it into some structure, you create conditions where there's, for example, a pocket where you can stick in a molecule. It's like a basket. Think of it that biology is creating very complicated baskets at the nanoscale, and these baskets have particular shapes which allow them to perform certain functions. So let me just go ahead to this point, since we're here, just to make it clear. Wait, this went up ahead. So 100 amino acids. There are, in 100 amino acids, I have 99 peptide bonds. I have 99 of those CONH. Okay, that's the building block, dipole with the backbone. There are, for each peptide bond, I have a phi and a psi. Okay, phi and psi are the two dihedral angles. So, if I assume that each angle can be in 3 states, there are this many number of configurations, and if each of these configurations is sampled, even in 1 femtosecond, you're never, ever going to find the folded structure of a protein. Yeah, please.
So, out of these configurations,
Yeah.
is there one configuration that is folded, or is there certain number of configurations that is folded?
There's an ensemble of microstates that are folded, but you'll see shortly that they exist in a very deep funnel. Okay, so there are many others, but there's the free energy landscape associated with the folded structure of protein is characterized by a deep funnel. So we'll see this shortly.
I think in this case, like, since folding, I don't know if it's like a real life folding.
Yes.
But it can be, I think, modeled by a simple rule that a certain angle
Yeah.
is determined by the angle before it. So kind of we have to go back, like we have to.
Yeah. So it's non-Markovian.
Yeah.
So and
It should have memory.
yeah, sure, indeed, and you'll see the manifestation of that in how if you looked at the thermodynamic landscape of the protein, you would see that it would have lots of. It's a very rough landscape with lots of minima until you reach the bottom, and so it has to go through all these minima before it goes into that deep minimum, which is essentially recasting what you're saying, but in terms of free energies. Yeah.
If the system has memory, I mean, why sum of over the possible states? I mean, since you are looking for some certain molecules which need to be stable or from a packet,
Yes.
why will you need to sum? Because I think summing over everything takes a lot of time.
Yes, and this is just the Gedanken experiment to say. Let's imagine this was random. It would not happen this way. Okay, because when people initially started thinking about, well, how and why does a protein fold, they wanted to know, is it random or not random? Is it happening in a restricted region of phase space or not? So these types of arguments allow you to rule out, different mechanisms. So let me go back to, okay, so these are the questions that we need to think about. So what are the physical and chemical rules that I can think about or derive to take a primary sequence of amino acids? So in the primary sequence, I know no knowledge of the three-dimensional structure, and how can I use that to predict what the three-dimensional structure is? So that's the first question. How do I understand why the protein folds so fast? And so remember we discussed the time scales of protein folding are between microseconds to milliseconds. Okay? So it's clearly not happening randomly. And finally, at the end of the day, if we want to understand why a protein spontaneously will fold, then I need to understand what's driving the enthalpic interactions, what's driving the entropic interactions. Okay, and the two compete in highly non-trivial ways, as you will shortly see. Okay, so those are the questions. Okay, so I'm just restating what I just said, going from. Okay, so this is less folded, going through an intermediate state, and then finally to some native structure. Okay, so you can see as you go from here to here, forget about these two in the middle, you're building more and more secondary structure. So you see here, you did not have the beta sheets, whereas here now you have 1, 2, 3, 4 beta sheets. So the folding process involves building more of these secondary structures into the morphology of the protein. Okay, what are the factors that, since we've discussed this a lot, we've talked about a lot of interactions now, what factors do I need to think about to understand the driving forces of protein folding? So I'll maybe put this, and then this should give you some hints. Yes?
Maybe the chemical surrounding. I don't.
Okay.
In a way that depending on what kind of, depending on the chemical elements surrounding a certain, maybe some primary structures.
Yes?
Then there may be, there's some changes that can occur that may lead to the folding of
So this is true. Can you be more specific? So broadly speaking, we have so this is my primary sequence. Okay? It has to pack somehow. This is polar, non-polar. Polar, non-polar. Polar means I like interactions with water. Non-polar means I don't like interactions with water. So, number one. So there's happy face with water. Sad face with water. So this is, let's say, let's call this the first factor. Second factor is what? So let's put this down. So there's interaction energies between the polar groups and water, and interaction energies with the non-polar groups in the water. So this is something that needs to come into, let's say, my model. If I want to think of some effective model, this has to be there, or at least we should think about it. What else? Well, if I pack a protein, there'll be also interactions between the polar groups with each other. Okay, these are favorable, possibly. I'll also have interaction energies between the polar and the non-polar groups. That might not be favorable. Okay, so these are the enthalpic side of the interactions, or the driving force. But then there's also entropy. Okay, so there's an entropy change of the protein, and there's an entropy change of the water. All these three factors are going to go into the delta G. So I need to know somehow all these different things. And just to give you a sense of these numbers, well, I don't need to put this down. So the delta G of protein folding has been measured both from theory and also from experiments. And the delta G for protein folding ranges between 0.5 to 7 kcals per mole. Okay, so this is on the order of kBt to 1 kBt to about 10 to 15 kBt, roughly. It's not so large. It's not large at all. If you think about all the different interactions that change when you do this, it's not that big a change. So remember, this delta G is going to be some summation of all these enthalpic terms minus T delta S. The fact that this is a small number is telling you something. It's telling you that in the protein folding process, enthalpy and entropy more or less balance each other out in the protein folding. And with a small preference on one side that ultimately drives the direction in which the protein will move. Okay, so this is the essential message here. This is probably very hard to see, but these are folding times of different proteins, and the delta G is associated with the protein folding. Okay, so these are for different types of sort of classical model proteins that have been used both in experiments and in theory in order to try and validate theoretical models. Now, just to make sure you understand this, is there any relationship between this folding time and this delta G? So, tau folding is the time it takes for the protein to fold. Delta G folding is what I just described to you here. Is there any relationship between this and this? Unfolded, folded. Delta G is the driving force. Okay, so delta G is this guy. The folding time is not related to this, it's related to this. Okay, they're two different things. So just keep this in mind. Okay? So this is about a rate of a process, how long or how slow it takes for the system to hop from this basin to this basin. That time is on the order of microseconds and milliseconds. The rate, that time, tau fold, is 1 over k fold, which is equal to, or it's proportional to, e to the minus beta of this activation barrier. This is Arrhenius law. Okay? Okay. So, just, you should have this at the back of your head, how to relate all these numbers to something in a simple two-state model. Okay? Okay. Are there questions before I move on?
Sure.
Yeah, please.
I don't know what you mean by, the entropy in the system, does it represent how, how disorder the, so
Yeah.
I don't understand what you mean by the energy balance in the,
Okay. Okay, good. So, let me maybe put this. Yeah? Okay. this delta G, let's put delta G0 so it's in the same notation. This delta G0 is this. The free energy difference between the unfolded and the folded. Okay, that delta G0 comes from an enthalpic change and an entropic change. This enthalpic change involves many different types of interactions. Okay, they are peptide water, peptide, everything there. But then there's also a change in the entropy. The change in the entropy involves a contribution coming from the protein, but also the change in the entropy of the environment, the water. And so what I'm saying is, we see that this delta G value is a small number. It's very easy to show. You take a simple protein with 50 amino acids, the change in the delta E, this part, will involve hundreds and hundreds of hydrogen, let's say, dipole-dipole interactions. So that can easily come up to several hundred kBt. This guy. So if this is several hundred kBt, but this is tens of kBt, this is telling you that these two changes are very large values that compensate each other to give a small number. Okay? So that's the argument. Okay, so I just want to show you, so that this might be an interesting presentation for someone if you want to talk about it. Let me. Yeah, okay, that's better. So, no, what did I do? I need this first. Yes. So first, I need to show you this. So this is a model that's used a lot in the statistical physics community. So as you know, lattice models are very popular in physics, and in the statistical physics community, people have been trying to think about, well, how do you rationalize the protein folding problem? Okay, what's the simplest model that you can come up with to rationalize why a protein would fold? Okay, do you really need to go through all these atomistic or molecular details? And so the one that's been proposed in the 90s, and there have been several extensions to it, is something known as the HP model. Okay, the HP model was developed by these two guys, and the model goes like the following. We put sites on a lattice. You can define the complexity of the lattice depending on how many amino acids there are, whether you want to do it in 1D or 2D or 3D. Of course, it gets more complicated as you move higher up in dimension. But you only think of two sites, polar and hydrophobic. Polar guys like water, H guys don't like water. And the essential argument behind the lattice model is that the reason why the protein wants to fold is hydrophobic interactions are favored. Because, remember what we discussed some time back, hydrophobic groups exposed to the water, you pay a penalty. So what does it do? It buries all the hydrophobic groups inside. So this model basically says, let's consider this type of a system and put favorable interactions to form an HH interaction, and then of course unfavorable interactions to put an HP So you can't see this, but I'll show you to an example. But each of these sites interacts with a bath. The bath is not on the lattice. Okay? And so, for example, if this is at the boundary of the lattice here, it interacts with the water, and so you pay a penalty. Okay, so there are essentially two interactions. There's, well, three. There's a hydrophobic, which is favorable. There's a penalty to form interactions between H and P that are not nearest neighbors. You'll see an example of this shortly. And if the H groups are at the boundary of the lattice, then they interact with the liquid. If they enter the liquid, you also pay a penalty. Okay, so that's the idea of the model. So I just want to show you just two examples of how this is sort of useful. Okay, I have to say I'm not a big fan of these types of models, but it's important to know. So let's switch to this. Okay. So and this is actually an example in the Roy Phillips textbook, and where he thinks about. Okay. So the system here is a 2x3 lattice. 2x3. Okay. Okay. I have in the sequence, I have 1, 2, 3, 4, 5, 6. There's 6 sites. Each of those 6 sites can take an H or a P. Okay? So there are 2 to the 6 possible sequences. Okay, fine. Now they say, well, let's consider 2 sequences and ask which of those sequences will form compact protein folded like structures. By protein folded like structures, those where the H groups are buried and close to each other. Okay, so that's the question. And so they consider 2 sequences. HP, 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 and another one which is PH, PP, HP. Okay, so just to make the connection for you, these are like the primary sequence of amino acids. Okay, in the real primary sequence of amino acids, I have at each site 20 possible combinations, so they're 20 to the power 6. This is impossible to even think about or manage with a type of model like this, but this model says let's coarse grain things, let's just separate things into 2 groups, H and P. Okay? And so they consider these 3 possible ways in which you can pack the sequence of 6 sites on a 2x3 lattice. Okay, so these are just possible examples of how you can pack the 6 sites with these 2 different sequences. Okay, so now we're going to ask the following question. If I put these sites, H and P, onto this, onto this, onto this, versus putting this here, here, or here, what will that do in terms of the total energy of my sequence? Okay, I haven't told you how you're going to compute the total energy. Okay, so okay, this is just to show you. Well, so actually, this is something I want you guys to try to do in class right now, and we'll also do it together. So for simplicity, yellow color, use whatever color you want, but I'm going to use yellow for H, and I'm going to use blue for P. And whenever there's an HP interaction that is not covalently linked, so this is a covalent link. Okay, so that's fixed. But if these two, if this was an H and this is a P, I'd pay a penalty, epsilon. Okay? And if the H is at the boundary, so if the H is here, it will also interact with the liquid. So there will be two possible interactions here. Where is the... Okay, so H, when H interacts with P, not as nearest neighbors, I pay an energy cost of epsilon. And when H is at the boundary, so for example, if H was here, I would pay a penalty. I'm going to assume also epsilon. And here, for example, the penalty would be 2 epsilon.
Excuse me, sir.
Yeah.
What do you mean by H at the P as nearest neighbor?
Say that again?
What do you mean by H at, sorry, the bond between H and P?
Okay. This, yeah. So, let me give you an example. So let's do this one first. So this is H, P, H, P, H, P. That's by definition. I'm defining the sequence to be that, so no surprise. Okay, so nearest neighbors like this, in the way that I've drawn it, they're covalently linked to each other. So I have no choice. So that's fixed. Okay? So what I mean by this thing here is that if I get an HP, for example, here, I pay an energetic cost of epsilon. If I have to put an H where it is interacting with the environment, I have to pay. Okay, so what I would like you to try and do with me is let's try and compute the energies associated with these 3 structures for these 2 different sequences. Okay, let's start with this one. Just a reminder, the polar group doesn't pay a penalty to interact with the environment. Okay, so I don't need that there. The H group has a penalty to play with the environment. Forming the HP, I pay a penalty. Okay, so let's try and experiment a bit, and then we'll see what we get. Okay. So I think this will help you. this guy is HP, HP, HP. So my color code here is yellow is H, blue is P. Where I have the dashed lines, you have a cost of epsilon. So each dashed line here corresponds to epsilon. So that's for this complex structure. Now you can repeat the same thing for this one and this one, for this sequence and that sequence. It's very easy, and tell me what you get. Wait, yeah, look. No. And we're setting there, let's say, the 0 to be this.
Because
It does react with water, but on this side only. This is, so the premise of the model is that H-H interactions are favorable. Okay, so without loss of generality, I can set that to 0.
because it seems like because these two have like similar I think in this case they all three do.
Perfect. Very good. Yes. Excellent. Okay, that's exactly the point. And so now you can ask, well, what is the Boltzmann weight? Right? Right. Okay, and then you can see as a function of temperature, how would that probability distribution change? So you can make a plot of temperature versus the probability, and see, as I increase temperature, what do I do to this population? Yes. Very good. Very good. This is for this one.
Yes.
Okay. Excellent. So now do this and that the same way. Yeah. Perfect. Excellent. Yeah. So what does this mean? This sequence, all the compact structures have equal probability.
Yeah.
Okay. Which is not what we want, at least from what we understand of protein folding. Protein folding, so in the first one, the probability of finding each state is 1/3. It's the same. But in reality, if we have the folded one being much lower in probability, much higher in probability, lower in free energy, then this sequence is not going to form a folded structure per se, because each of these compact structures have the same probability. But now if you repeat the same thing for this, you'll see that this is not the case. This one is included, yes. That one, perfect. Yeah, because this is with the environment, so there's a penalty. Okay, so you get 7 epsilon. Perfect. Okay, very good. Great. So now compare these two for 2 and 3. The same way. Yeah.
No, just a question.
The sequence is fixed before folding.
The sequence is fixed before folding, always.
Okay, so if the sequence is fixed, then let's say if we have six amino acids,
Yeah.
then we should find the optimal solution within like 6x6 block, because
Yeah. Absolutely. So basically, what we're doing here is
because I don't think we can fix the 2x3 box.
You're right. You're absolutely right. So to do it correctly, you'd have to have a 6x6
Yeah, obviously the linear and the other stuff,
Yeah.
we can rule them out, but
Yes. No. So what we're doing here is we're essentially reducing the effective entropy, the volume that the sequences can sample. But it's to make a point, okay? But you're right. But it becomes horribly
large.
yes to do it on big lattices. Huh? Excellent. Good. So do the next one. What did you get? How? Okay, good. This is sequence A, sequence B. Okay, now do sequence 3. Well, not sequence 3, but compact structure 3. Okay, so there's a penalty, an energetic penalty, to keep the H near the boundary of the lattice, because it's now, in this model, it's interacting with the liquid. This doesn't like the liquids. So I have an epsilon and an epsilon here. I have an epsilon there, so this is 4 epsilon. Then I have 5, 6, 7. So the total energy of this, take it 7 epsilon. Okay, so now repeat this same exercise, getting these numbers for the second compact structure.
Will it be like a partial chain with you? That is another space to
Yeah?
to form a partial model.
Okay, good, excellent. Exactly. Exactly. Perfect.
So, like what you said,
Yeah.
you asked you about this is fixed beforehand, I mean the sequence.
Yeah,
But then this is not the only possible.
I know.
reason.
I know. You're right. So to do it absolutely correctly, I should put it in a 6x6 lattice, and then I should do it in 3 dimensions. So it would be horribly difficult to compute all those things, or to show them. So this is just to make a, let's say, proof of concept, that depending on the sequence, you change the Boltzmann weight of finding different configurations, and very small differences in the sequence of H versus P can change drastically the whole physics of the problem. This is one point. Second point, I mean, are you sad? Well, okay, you've already addressed one issue, which is we should not be satisfied with this model, because I've essentially cut out the entropic, the phase space that I'm allowed for the configuration sample. But what else is missing from this picture? What are the assumptions that I made, and what?
The nearest neighbor interactions.
Nearest neighbor interactions. Yes, absolutely. Is this a reasonable assumption to make? Probably not. Probably not. You have to remember that, okay, these guys, you could say, non-polar, hydrophobic, they only interact through van der Waals type interactions. But these guys have long-range electrostatic interactions with each other. So, in reality, these guys are also interacting. These are interacting. These can interact differently with the bath. So if you start digging into the details, then getting quantitative models that describe the protein folding process will need all these types of detail. That's one point. Second point, well, I don't know how many have finished, but here we're just looking at thermodynamics. So for example, the probability of finding each of these microstates is e to the minus 7 epsilon over the partition function, which is 3 times e to the minus 7 epsilon, which is 1 over 3. Okay, so equal probability for this one. For this one, you guys have already seen, this one is e to the minus beta 2 epsilon. This one is 4 and 4. Okay, so the Boltzmann weight in this sequence for this guy is very different compared to the others. And this is a really interesting, so what I like about this is it allows you to see in a very easy manner, just for 6 amino acids, you change, let's see there, yeah, a system which has the same number of polar and hydrophobic groups, you change the ordering, and you sensitively change the thermodynamic landscape. Okay, and this is what happens in biology. Okay. Okay, so you should know how to, be able to just use these types of simple models to predict something like the partition function of it, the probability of one state versus another, the heat capacity. Okay? Okay. Questions before we end for today? So next week we have regular class on Tuesday and Thursday, but I want to make up for the class on Tuesday. So what are your schedules like? You have an exam on Wednesday. Okay. So fine. So then let's do Friday. We'll schedule a class Friday morning then again. Is that okay? Okay. So Friday morning, I'll tell participants at 9 a.m. Okay.
By the way, if the protein folding process is not a random process,
Yeah.
what is it? What kind
It's directed.
Are you free on Friday? No.
Where is my chalk? Here we go.
I hope you have an event on Friday morning.
Yes. You do have an event, and I have an event on Friday morning involving you. This is at what time, though?
10.
It's at 10. Okay. Let's do the following. We can meet either earlier, from 8:30 to 10, or we can meet from 11 to 12:30. Which is better for you? What's 11 to 12:30? Raise your hand.
We need to check the schedule.
Yeah, can you please check? So to answer your question, so the protein folding landscape has this deep funnel-like structure, and so you start from somewhere here, and then you slowly go on some directed pathways that force the system to move to the minimum. So it's not moving in a flat potential, and then all of a sudden, Okay, so this is why it's much faster. Not random.
Oh shit.
Okay, what's the schedule?
We're free on the
You're free at 11. So 11 to 12:30. Raise your hands. Okay, majority wins. Everyone. No, we could meet at 8:30.
too early.
It's not a problem for me.